Hello, welcome back to CS128 Honors. I'm William, or Eustis, and we'll go ahead and get started with our lecture today. I believe this is lecture number 7, and so we'll get right into it. Let me just double check to make sure my drawing tool is working, and let me fix it real quick since it's not. Okay, there we go. Awesome. All right, so the major goals for today is going to be teaching you the basic idea, the concepts of this idea called ownership. And in fact, the next 3 lectures, this one included, so I guess maybe the next 2, are all going to be discussing ownership. This first one, I'm basically just here to give you the understanding, the conceptual knowledge of what ownership is and why we use it. Next lecture, Matt is actually going to be discussing some of the more thorough implementations of ownership, how it works with functions, how we can kind of work around it a little bit every now and then to make our lives slightly easier, and stuff like that. And then the third lecture will just be me only doing examples of ownership, times when it's useful, just so that y'all can get really, really comfortable with the idea. So that'll be a very kind of code-heavy lecture that next Monday. But without further ado, we'll go ahead and get started. And once again, these slides are based off of the Russell Lang book. So if you ever want to follow along, I encourage you to look there. Quick reminders, MP0 is due tonight at 11:59 p.m. Yep. Homework 1 is due on Thursday. We have it Thursday instead of Wednesday since I think we released it a day early. So we're giving you all an extra day. So make sure to do those. And then I believe MP1 is releasing this Wednesday. So Matt will talk about that. And we'll discuss the ins and outs of that, I guess, at that point. I'll also probably talk more about it during the Code Heavy Monday lecture. So expect some extra discussion on MP1 during that time. And it'll be due 2 weeks after the release date. Okay, so let's start to kind of introduce the general idea of ownership here, why we actually use it and why it's necessary. So all languages are going to require some level of memory management. And that is to say, when we create some data that we need to keep track of, we also need to make sure that we're getting rid of that data at some point. Ideally as soon as possible, but no sooner. Right? If we get rid of it too soon, then what we're going to end up doing is accessing data that has been what we say deallocated, and it could be garbage data. We really have no guarantee of anything that is there, and it can be data that is not the true data that we're expecting. Similarly, if we hold on to it for too long, our certain programs and maybe the programs that you're writing can very quickly sort of run out of space. If you've ever heard of sort of memory leaks in various games and programs, this is a great example of that, which is they're allocating some information, they're allocating some data, but they're not getting rid of it. And so what it's doing is it's just slowly building up more and more space until you run out of space and the program crashes. So obviously both of those are sort of critical failures. You can think, for example, if we didn't have a great way to manage memory in either case, and this was sort of a more common problem, critical systems would be failing all the time and bad things would happen. So there's a couple major approaches that we use to manage memory. One of the first ways is garbage collection, which are used commonly in Lisp and JavaScript. And basically this has the general idea of saying, when we detect that this memory is no longer being used, we'll stop keeping track of it. One moment. Okay, apologies about that. And then next is we allow the programmer to do it in certain languages. So in languages like C, C++, you might know about malloc, new, delete, stuff like that. And that's basically saying, okay, the program's not going to worry about creating and destroying memory. We're going to let the user worry about creating and destroying memory. And if they mess it up, they mess it up. But it's up to them to kind of ensure that any memory they create is eventually getting destroyed. This has certain positives. You have more control. But unfortunately, programming can be hard sometimes, and there can be sneaky edge cases where things can slip away, and then you end up having a memory leak. And then there's this third idea that we're going to call ownership in Rust. And it sort of ties the two together, and it's sort of its own concept. And that's what we're learning about today. And so one thing that I want to kind of reiterate or drive home is the concept of ownership in and of itself is sort of very easy to understand. It's not too complex, but it is very important to know. And in fact, when you're coding in Rust, the better you get at it, eventually you'll just have to pay no attention to it since you'll understand. But it is something you have to pay attention to as you're going, and especially once we get to more complex problems. Okay, so let me introduce the three major rules of ownership. First, each value in Rust has a variable called its owner. So saying we have, some value here, maybe a string, right? If we have like let x equal hello, x is the owner of the hello data. There can only ever be one owner. So if we, we'll get to this example later, but x is the only owner of this data. There can never be a multiple owners. And then when the owner goes out of scope, so if we have some extra curly brackets here, once we get here, this value, this data is actually dropped. We get rid of it. We no longer have access to it. And so let's just do some quick refreshers on how scope actually works. So given we have our main function here, we'll create an inner scope. And if any of you are wondering, you can pretty much always just sort of add semicolons to go in and out of scope of things. Usually it's not necessarily very useful, but this is basically what we're doing here is we're just entering some other scope. In this scope, we'll initialize x to be 5. If we look right here, x is not in scope since it's not initialized. At this point, x is in scope and is initialized, so we can use it. But once we leave the scope, once we leave these curly brackets, then x is no longer in scope, and we don't have access to it. So if we tried to do, for example, like println x, it would say, hey, this value x doesn't actually exist. I don't know what you're talking about. And it's the exact same for string literals. So for example, if we have the string hello, it's the exact same. There's no difference. And let me give a quick refresher on this idea of stack and heap. And this is something you'll learn about more in CS128 and CS225 and in various classes. And I just want to kind of give you a very basic understanding, since it's going to help with a couple of the concepts we're learning about. And honestly, maybe it'll help you when you learn about those later. So when we run a program, this is what happens in memory. We have, our low memory address is here and our high memory address is here. Not that the order totally matters. And basically, we have three regions that I want to kind of point focus to. First, the region here is holding things like global variables, the program data itself, so what needs to actually run, and various other things that I won't get into. And then I want to point out kind of two very important sections here, the heap and the stack. The stack is where we're storing all of our local variables that have kind of a fixed size like this, x equals hello. And the heap is where we can allocate objects to. And in fact, let's sort of look at an entry on the stack. I'm not going to get into these, so these are all different kind of register values that we're not going to get into since that's way outside of the scope of this class. But what I will point out is some of these are sort of very familiar. For example, on the stack are passed all of the parameters to the function that you enter. Also is passed the memory address of the next instruction. So eventually, once we finish the main function, actually the main function is maybe not a great example here, but if this was some other function that was called from main, this return address is going to be basically the line that we've called it the other function from. So if this was, for example, other. Maybe I should have drawn this example a little bit cleaner, but basically this return address is where we want to go back. And then more importantly, the ones I really want to pay some extra attention to are these local variables. So local variables are, of course, things that we're creating as we're going. So let x equals hello, this is a local variable. And there's some important kind of critical details about stuff that is on the stack. So values on the stack are going to have a known fixed size. So what are some examples of things that have a known fixed size? Well, string literals, for example, right? Values like ints and floats and things like that. Additionally, we learned about some of the data structures in last lecture. If you remember, arrays have a known fixed size. Tuples have a known fixed size. And so all of these things are things that go on the stack in Rust. But not everything can go on the stack. There's a very kind of important usage for things on the heap as well, when we need to have things that we don't know the size of, right? Vectors, I think, are a prime example. Another example is this string class that we can differentiate from the kind of str string literal type. This is the string class or the string object or whatever you want to call it. And this is kind of a prime example on why or how they're mutable. We have functions like push string, which are just appending, extra data onto this string. And so if we actually look at what happens here, we call the string from function. And what it's actually going to do is allocate us a little piece of memory within the heap that's going to store this data. And then the value of x is going to be the location of this data, right? While, sort of in reference, when we were working with the stack, we kind of have all of the locations and references right here. So it's less complex. We can kind of directly read these addresses. But here we first need to kind of go find this location and then read the data. And of course, we can also edit the data there. Since we have this block of memory, we can also add world. I won't try to fit it in that small block, but hopefully you get the idea. Okay, so one more time, just to draw the distinction, local variables that have a fixed known size are usually going to be local variables and are going to be on the stack. While things that are mutable, often it's going to be more complex classes and objects. Those are going to be initialized on the heap, because they might change in how large they are, or what data they're storing, or how they're storing that data, or many other things. Okay, and now we're gonna start tying together why this is important. So when we exit the scope, the stack is automatically torn down. And what we mean by that is if you want to get into I'm actually electrical and computer engineering, so I can tell you the specifics of it, but quite literally, we just forget about these values. We take the return address as the next address we want to execute, and then down here is the same kind of stack for whatever function this return address points to. That's really quite literally what's happening. And so the next instruction is pointed by this return address. This return address, or this function, we'll say the main function if this is the other function, has its own local variables, has its own parameters, etc. Okay? So the stack is automatically torn down when we leave the scope. However, the heap remains. And there's a couple important reasons why the heap remains. And so we do need to get rid of it. And the way Rust handles this with ownership is Rust is going to drop the data, which is what we call deleting things from the heap in Rust, when the owner leaves the scope. Okay, and so let's look at what this means. We initialize some data on the heap, and we have x point to it. So right here is where x points to. This little piece of data right here, we'll say. We adjust the data on the heap. Again, this is a variable size, so we can add stuff to it without kind of worry. In Rust, we'll handle the case. Let's just say for a moment this block is maybe not big enough for the whole thing. Rust automatically will handle, and the compiler will handle eventually extending that to be a bigger size if you need it. Okay, and then the owner of x is the owner of this data. And eventually, x is going to leave scope. And when x leaves scope, we're going to delete this data automatically because the owner has left scope. And that's it. That's really the core idea of ownership. And we're going to look at some examples on why this really matters and how this matters in a second. And kind of the core reason or the core time we need to be worried about this is when we start doing stuff like this. So this is, once again, this is on the stack because we have, literal values, constants, basically. So first we say let x equal 5. We have local variable equal to 5. And literally the binary in this location is going to be binary for 5. And then we say let y equal x. And what we'll do is we'll take the data here and we'll copy it into here. And so this will also equal binary 5. And then we can easily change x to be equal to 6. And we know that, this value is going to change to 6, and this value will remain 5, right? However, And this is kind of the important distinction. What's going to happen now? Because if we remember, S1, the string, actually is the location of this data in the heap, right? And so when we say let S2 equal S1, we sort of have a couple different options. And let's visualize this one more time. So this is S1 here. This is what we're working with. And it has a couple things. It has the capacity, being, how many places the string can hold, which can change if we need more with, the append string stuff. It has the current length of the string, and it has a pointer to the data. And then this data here, this is in the heap. These are locations on the heap. We can think, this right here is H, this right here is E. You get the idea. I won't be able to fit all the letters. And so when we do S2 equals S1, we have two different options on what can occur. In the first case, actually, let's explore the second case first. So in the second case, this is what we might call a deep copy, which is to say we're going to go into the data inside of the pointer and copy all of the values to a new place. Now, there's a couple reasons why this isn't ideal. First of all, it's extremely slow, or can be extremely slow. And in reference to, things on the stack, it is extremely slow. And especially when you have maybe very, very large objects on the heap and objects that, maybe instead of an H, this is a whole nother string that has its own thing on the heap. Things can get messy pretty fast because you have to kind of recursively make sure you're copying each and every part of it. And so that's not really ideal. Additionally, just the fact that we want to be able to kind of work with the same thing, right? If we, for example, said like S1 equals some new value, we might want that to be reflected in S2 as well, since they're technically talking about the same object. And that is what occurs in this example here. We can see what this does is it has both values point to the same location on the heap that has the same data. And in this case, what will happen if we say, for example, S1, we change the first character instead of an H to be, an X. The value, if you were to check the value of S2, or the value of the data S2 points to, is going to have that X, since they're pointing to the same data in the end. However, this also raises a problem. Do you remember how I said when we leave scope that all of the values are dropped? Well, this will happen. And in fact, what will happen here is we leave the scope and the value of S1 is dropped. So this data is deallocated. And then the value of S2 is dropped. And so this data is attempted to be deallocated a second time. And of course, that's not quite how that works. You can't quite do that because you don't own that data anymore. Some other program might be using that, or some other object might be living there. And so you actually aren't, this will throw an error and bad things will happen and your program will explode and your computer will catch on fire, which, obviously is not ideal. And so this also causes a problem. Okay, so what's the solution? Well, it's kind of neither. The whole idea about ownership, if we remember, is that there can only ever be one owner. And so when we assign S2 to S1, we actually pretty much get rid of the ability for S1 to reference this data. S1 no longer owns this data. It cannot edit it. And so if we were to, example, try to print the value of S1 like this, we'll actually receive an error. We'll say, hey, you can't read that. That's not your value anymore. And this error I want to get a little bit more into, because it says move occurs because S1 has type string, which does not implement the copy trait. And it says the value is moved here. And in fact, one more thing I just want to mention, we actually call this moving, while previously we kind of referred to the things as deep or shallow copies. So this is a shallow copy, meaning it's only copying the value of kind of this here. This is a deep copy, meaning it's copying all the values inside of here. Instead of a copy, this is a move. We're moving essentially the data from here into here. Okay. So it says move, value was moved here. String doesn't have the copy trait. Well, what does this copy trait actually mean? We won't get too far into traits in this class, since it's a little bit outside the scope of what we'll be teaching. But traits are basically core functionality of certain data types inside of Rust. And in fact, the copy trait means that when you assign a new value to some old value, the copy trait dictates whether or not this old value is going to be accessible still. And in fact, we know, for example, if we said, let x equal 5 and let y equal x, we know that x still has access to 5. And so this almost seems for a moment like a counterexample. Like, Eustis, this ownership idea is not true. This clearly works and nothing bad happens. That's because ints have this copy trait. And what's happening is the data from 5 is being copied into y. While, in terms of these strings, we can't necessarily have a copy trait because we don't know if we want a shallow copy or a deep copy. And so instead we have the idea of ownership that will handle it. Okay, now on the other side, if we try to print S2, it'll of course work flawlessly. Nothing too crazy there, no tricks, no extra kind of craziness. And if you're curious about all the things that have the copy traits in Rust, it's sort of not too surprising. It's basically all the things that have fixed values that can go on the stack. So all of the integer types, all of the Boolean types, floating point types, the character type, so chars. Additionally, tuples, because tuples have a fixed size. And then when we get to string literal and borrowing strings, we'll talk about that more, or Matt will talk about that more in next lecture. And then one thing to remind yourself with tuples is the values in the tuple must have the copy trait. So if you have a tuple of like I32, you're good to go. It's not my best 2, but that's okay. But if you have one of the string type, you're obviously not good to go, right? Because who knows what the correct behavior is there. Okay. And so you might now ask yourself, we have some, we'll say let x equal string from, for the sake of not writing more things, I'm just going to have it be a single string A. You might ask yourself, okay, does this mean we can never kind of refer to x as different things? Like we can never have some other variable that might explore x that we're passing to some different function while we do something else with x? Or, are we kind of stuck? Well, the answer is actually no. And there is sort of this idea of borrowing that Matt's going to discuss in next lecture and that we'll explore even more on Monday's lecture. That allows us to kind of not worry so much about this. And in fact, a lot of you have kind of already referenced this or already ran into this. And in fact, when we do borrowing, what we do is we create a reference to that thing. And so if you've seen in your code or maybe in the examples that the Rust compiler has suggested you do to fix certain things, you might have seen, hey, consider borrowing this value, or hey, consider throwing an ampersand at the beginning of some statement. And the reason for that is because you need to borrow the value first. So it's been a little bit common. You've probably interacted with ownership indirectly already, but hopefully now we're starting to sort of uncover the hood on how it actually works and what's actually going on, and so you understand it a little bit better. Okay, so final reminders, don't forget, MP0 is due tonight. MP1 will be released on Wednesday. Homework 1 will be due on Thursday. MP1 will cover, all sorts of stuff. A lot of it will be stuff like ownership. We're now going to assume that, you're better at programming in Rust. And so these MPs are going to get harder. So for those of you who, might have waited until last minute for MP0, I highly recommend you do not do that for this one. We didn't create checkpoints, but I highly encourage you all to, make some significant progress in the first week at least, because, you never know if you have a midterm or if there's some event that you'd like to go to instead. So don't wait until last minute. These next MPs are going to start getting a little bit longer. Have a great time, and don't forget to come to office hours. We're always here to help, or just ask a question on the Discord. Okay, have a wonderful week, y'all. I hope you learned a lot about ownership, and I'll see you on Monday.